Hi everybody. So in this video we continue with chapter 9, vectors, lines, and planes, specifically section 9.3, vector cross product. So in several applications of vectors, there's a need to find a vector that is orthogonal to two given vectors. Now remember that this means perpendicular. In this section, we will discuss a type of vector multiplication that can be used for this purpose. So if we have a vector u and a vector v, the cross product, which is written as u times v with the x sign, is defined as u2 times v3 minus v2 times u3 times I minus u1 times v3 minus v1 times u3 times j plus u1 times v2 minus v1 times u2 times k. Now, an easier way, in my opinion, is using the properties of determinants, and the definition would be equivalent. Now, what does this mean? U times V. What you do is this. You know that you have to cross multiply the components that are not in the same column as I. So we would do it with these, right? So it would be U2 times V3 minus V2 times U3, and the result of this times I. Then for J, we go minus, and we do the same thing, but with the components that are not in the same column as J. So then it would be U1 times V3 minus V1 times U3, and this times J, and then finally plus, and we do the same thing for K. We would cross multiply the components that are not in the same column as K. So plus U1 times V2 minus V1 times U2, and this times K. So notice that this is the same definition we see over here to the right. So now let's do example 9.14, and it says, given the vectors U and V, find A, U times V. So this is the cross product of U and V. So remember that this is what we do. The first row is going to be I, J, and K. Now, because U is first, the second row is going to be the components of vector U, which are 2, -3, and 1. And then next we write the components of vector V, which are going to be 1, 3, and -2. So this is going to equal, now remember that for the first one, we grab the components that are not in the same column as I. So this would be -3, 1, 3, and -2. And we do the cross product of these and multiply that by I. And then we do minus, and then for J, the components that are not in the same column as J, so that would be 2, 1, 1, and -2. Cross product of that times J, and then plus, and the same thing with K, right? So 2 minus 3, 1, and 3, and this times K. So here, if you do the math, you're going to get 3I plus 5J plus 9K. And that would be the answer for letter A. Now this vector would be perpendicular to U and V, or orthogonal, right? So B is the opposite of this. It's going to be V times U. So here, the order is going to change, right? Because we have I, J, and K, but now we exchange the order here with the rows. We start with V, so 1, 3, minus 2, and then vector U would be 2, minus 3, and 1. So this is going to equal 3, -2, and then -3 and 1 times I minus 1, -2, 2 and 1 for J plus 1, 3 2, and negative 3 for k. So if we do this, we're going to get minus 3i, minus 5j, and minus 9k. Now, if you look, notice that we're going to get a relationship here, and that is that the cross product of u times v is equal to minus the cross product of v times u. Then C, they want us to find u times u. So that is the cross product of a vector with itself, right? So notice that here we are going to get I, j, k, and then we have to write the components of u, of vector u 2 times. So 2 minus 3 and 1, and then 2 minus 3 and 1. And then here we're going to get something interesting. We're going to get negative 3 and 1, negative 3 and 1, and this times I, minus 2, 1, 2, 1, and this times j, plus 2 minus 3, 2 minus 3 for k. And notice that if you do these cross multiplications, they're all going to be 0, right? This is going to be 0i, this is going to be 0j, and this is going to be 0k. Therefore, this equals 0, and this is another property of the cross product of vectors, which we're going to talk about next. So in the next slide, you're going to find these properties. If two rows of a determinant are proportional, then the value of that determinant is 0. So for example, if you have a vector u that is equal to ai plus bj plus ck, and a vector v that is m times ai plus m times bj plus m times ck, then you get that the determinant is equal to 0. So this result leads to an important property of vector products. Two non-zero vectors are parallel if their cross product is 0. And the second property is if two rows of a determinant are interchanged, then the determinant's value is multiplied by negative 1. So that means that if you have u times v, that's going to equal minus v times u, as we saw in the previous example. So recall that the cross product of u and v is a vector that is perpendicular to both u and v, and it obeys the right-hand rule, as you can see in this illustration here to the left. And then it has a magnitude of the absolute value of u times v, which is the modulus of u times v, and this is equal to the magnitude of u times the magnitude of v times the sine of the angle between the vectors. Now also recall that u times v is equal to minus v times u. And you can see this opposite vector over here. So it's also perpendicular, but opposite in direction. Now, recall that the area of a parallelogram is base times height, but we can determine the height using the magnitude of v times the absolute value of the sine of the angle. As we can see here, this is just simple trigonometry, right? So that means that the magnitude of u times v will give us the area of the parallelogram that is formed by the vectors v and u. So we continue with example 9.15, and it says find a unit vector orthogonal to both vectors u and v. Now, a vector that is orthogonal would be u times v, which we did before for these two vectors. And remember that from the previous example, it was 3i plus 5j plus 9k. But we would have to divide this by its magnitude if we want to get the unit vector. So we need the magnitude of u times v, and that's going to be the square root of 9 plus 25 plus 81, which is equal to the square root of 115. So we have the unit vector that is orthogonal to both u and v, and that's going to be u times v divided by its magnitude. Therefore, it's going to be 3i plus 5j plus 9k divided by the square root of 115. So we continue with example 9.16, and part A says, show that the quadrilateral ABCD with its vertices at the points A, 302, B, 625, C, 122, and D, 445 is a parallelogram. And then B, find the area of the parallelogram. Okay, so before we do this, you have to take into account where these points are in the three-dimensional plane, because we're tempted to write the vertices in order, right? Whether it's clockwise or counterclockwise. But in reality, we have to imagine where they are in the 3D plane. So notice that in the 3D plane, they are not consecutive, right? So it's A, B, D, C. But let's see if this is a parallelogram, although it seems to be one, but we have to prove it, right? So what is vector AB? So AB should be equal to CD, right? AB should be equal to CD if they are parallel. So AB, remember that it's going to be B minus A, and that's going to give us 6 minus 3, that's 3, 2 minus 0 is 2, and 5 minus 2 is 3. So this should equal vector CD. So D minus C. And notice that, yes, it's going to be 4 minus 1, which is 3, 4 minus 2, which is 2, and 5 minus 2, which is 3. So yes, these are parallel. Now, let's see if AC over here, and DB are parallel. So vector AC is going to be -2, 2, and 0, and this should equal vector BD, which we can see is in effect -2, 2, and 0. So we have proven part A. This is a parallelogram. Now we need to find the area, and for that we need the magnitude of the cross product of two vectors that are adjacent. So for example, AB and BD. So first of all, let's find the cross product of AB and BD. So notice that this is going to equal the matrix, right? The determinant. So I, J, K, and then 3, 2, 3 for vector AB, and -2, 2, 0 for vector BD. So this is going to give us -6I -6J plus 10K if you do the math. Now you can also write it in vectorial form, right? So you can write it as -6, -6, 10. Then we need the magnitude, because the magnitude of the cross product is going to give us the area of the parallelogram, right? So we need the magnitude of the cross product of AB and BD. And that's simply going to be the square root of 36 plus 36 plus 100, and this equals the square root of 172, which can be simplified to 2 times the square root of 43. So next we have example 9.17, and it says, find the area of the triangle determined by the points A, 2, 2, 0, B, -1, 0, and 2, and C, 0, 4, 3. Now here we don't have the problem that we had before, right? It doesn't really matter where these points are, because we know that whether this is A and this is B and this is C, or this is C and this is B, we are going to have two sides that are adjacent, which can be AC and AB. So that means that we can find vectors AB, which is -3, -2, and 2, and vector AC, which is going to be -2, 2, 3. And then all we have to do to find the area is do 1/2 times the magnitude of the cross product of these two vectors, right? Okay, so what is the cross product of the two vectors? Let's find that first. So AB times AC. And if you do the math, you already know how to do this. So this is going to be -10, 5, and -10. So that means that the area is going to equal 1/2 times the square root of 100 plus 25 plus 100, which is 1/2 the square root of 225, and that's 1/2 times 15, which is going to be 15/2. So in the next slide, you're going to find a concept called the scalar triple product. And this product is very useful in its geometric interpretation because it's going to be of great help in finding the equation of a plane later on in this chapter. So basically, if you have three vectors, u, v, and w, the scalar triple product is going to be the dot product of u times the cross product of v and w. But basically, you end up with this determinant. This is going to be very clear in the next example. Okay, so let's take a look at example 9.18, and it says calculate the scalar triple product of these three vectors, right? So we write it like this, and it's going to be the determinant of these three vectors. So first we write the components of vector u, so 2, -1, -5, the components of vector v, which are 2, 5, and -5, and the components of vector w, which are 1, 4, and 3. So this is going to equal, and this would be the same as the other determinants we've been doing, right? So this is going to be 5 times 3 minus 4 times -5, and this times 2, minus 2 times 3 minus 1 times -5, and this times -1, and then plus 2 times 4 minus 1 times 5, and this times -5. So then from here we're going to get 15 plus 20 times 2 minus 6 plus 5 times -1 plus 8 minus 5 times -5. And this is going to give us 70 plus 11 minus 15, which equals 66. So in the next slide, you're going to find something that says geometric interpretation. And basically what it says is that the absolute value of the triple scalar product is going to give you the volume of the parallelepiped. So this word is hard to pronounce, parallelepiped, that has three vectors as adjacent edges. So a parallelepiped is this shape you see here, this three-dimensional cuboid type shape, which has the three vectors as adjacent edges. So we end this video with example 9.19, and it says, consider the three vectors, and they give us three vectors u, v, and w. And part A, find the volume of the parallelepiped that has these vectors as sides. Now they should say that these vectors are adjacent, but that's okay. So let's do part A. Now, first of all, let's find the triple scalar product. So this would be this, right? Which is the determinant that would be made up of the components of u, which are 2, 1, and m, the components of V, which are 3, 2, and 3, and the components of W, which are M, 2, and 1. And then we just do the determinant, right? So this would be 2 times 1 minus 2 times 3, and this times 2, right? So notice it's this times this, minus this times this, times this. And then minus 3 times 1 minus m times 3 times 1. This times this, minus this times this times this. And then plus 3 times 2 minus m times 2 times m. And then from here, we're going to get 2 minus 6 times 2 minus 3 minus 3m times 1 plus 6 minus 2m times m. And then from here, we're going to get minus 8 minus 3 plus 3m plus 6m minus 2m squared. And then if we add similar terms and we reorganize this, we're going to get minus 2m squared plus 9m minus 11. But the volume is going to be the absolute value of this, right? So the volume is going to be the absolute value of minus 2m squared plus 9m minus 11. Now for part B, they want us to show that these vectors can never be on the same plane. So if you studied the previous slide, then you will know that this can only happen if the volume is equal to 0, right? Because if they are on the same plane, then there's no volume. In other words, we would have that the triple scalar product is equal to 0. So minus 2m squared plus 9m minus 11 should equal 0. So if these vectors cannot be on the same plane, then this would have no real solutions. In other words, the discriminant should be, if it has solutions, it should be greater than 0, right? In other words, b squared minus 4ac should be greater than 0 if it has solutions, real solutions. But notice that this is going to give us 81 minus 88. And this is obviously equal to negative 7, which is less than 0. Therefore, we can say that the three vectors can never be coplanar.